for disappointing you. Yeah, I've been a little busy. So, okay. So last class we were talking about trying to find the antiderivatives of integrals that involve trig expressions, right? Sines and cosines specifically. Oh, that's not it. Why does this look so small? There we go. So what we still need to deal with now is some sort of strategy for attacking integrals that have tangents and secants in them. All right? Tangents and secants. So just like we had with last class, we had the Pythagorean identity, right? We used sine squared x plus cosine squared x was equal to 1. What are the other two Pythagorean identities? Okay, so that was a power reducing. We had that one, right? But I'm saying there's two other. Yeah, divide everything by sine squared, so you get like 1 plus cotangent squared x equals cosecant squared x, and then the other one is divide everything by cosine, so squared, so tangent squared x plus 1 equals secant squared x. So those are your three main Pythagorean identities from pre-cal. And the one that we used last class was this one. We used that one quite a bit. Now we're about to use this one. So remember, that one that I boxed has like three different versions. You can solve it for secant squared, you can solve it for tangent squared, you can solve it for 1, right? Those are the three different ways you could look at that. So whenever we're trying to do a problem that has secants and tangents in it, if we see tangent to a power, secant to a power, and the power on secant is even, we're going to be using this identity here, okay? Solving for factoring out a secant squared. You'll see as I go through it. If we see secant and tangent together with an odd on the tangent, then we're going to factor out a secant tangent. So let's just do a couple of examples and you'll see how this is going to go. First one is integral, let's see, tangent to the fourth x secant to the fourth x dx. All right. So let's do this. Now let's remember a couple of things. We already know that the derivative of tangent is what? What's the derivative of tangent? Secant squared x, right? And then what's the derivative of secant? Secant x tangent x. Okay, so those are things we know. We're very comfortable and familiar with these two. So what we're going to do is look at these. We have a power on the tangent, power on the secant, and we notice that the secant has an even power, right? Whenever we see an even power on the secant, what we're going to do is we're going to peel off two powers of secant. So we're going to peel off a secant squared. So we rewrite the secant to the fourth as secant squared times secant squared. Now the reason we do that is because this secant squared right here, secant squared x dx, that's the derivative of what? Tangent. That's derivative of tangent, right? So if I can somehow rewrite everything over here with tangents in it, then I'm in business, right? Because then I can let u be tangent, and then here's the derivative. So this already has tangent. How can I rewrite secant squared x using tangent? Yeah, just right here. This is it. So I can rewrite this as tangent to the fourth x times secant squared x, which is tangent squared x plus 1, and then secant squared x dx. Yes?
You wouldn't put it just the squared on the outside of the parentheses?
No, because this is not the same as this. This would mean FOIL it, and then you get tangent squared x plus 2 tangent x plus 1. That's different than, yeah, all we're doing is replacing that piece with what it is over here in the identity. Okay, so now we have, this is the derivative of tangent, and everything in here has tangents or constants. So we should be able to make a basic u substitution now. The u substitution is what? U is tangent x. And the derivative of that we already know is secant squared x dx, which we have exactly. So now we can rewrite the entire integral in terms of u. So this would be integral, what? U to the fourth, parenthesis, u squared plus 1, and then the very end of it, du. That's it. And that one we could do just how? Distribute the u to the fourth through, right? So algebraically, this is going to clean up pretty nice. Distributing u to the fourth, and now that's just power rule, right? So we've got 1/7 u to the 7th plus 1/5 u to the 5th, and then plus c, and then we replace u with tangent. So replace the u with tangent of x, and we're done. How does that seem? Okay?
That's fine.
All right, let's look at the next type that we're going to do here. So what happens if we change this to 5th power and 3rd power? So first let me show you, I wouldn't necessarily write this down, but let me show you why what we just did won't work. Okay, so if we do what we just did, don't write this down. If I peel off a secant squared, I'll only have one secant here because it's odd, right? So I would have like that. And this here is still the derivative of tangent, yes? Mm-hmm. So if I could get everything over here in terms of tangent, I'd be in business. Problem is what? I have secant x, not secant squared x. And so if this was even, right, if I pull two of them off, I'm always going to be left with an even amount of them here. And that means I could always go to this identity. But because that's to the 1st power, I don't have an identity to go from secant over to tangent. All right? So I won't be able to convert. Y'all see why that doesn't work? So what we're going to do instead is we're going to use this right here. So I know that I have, at least since this is odd, I have one secant that I can peel off, right? And I'm assuming I had a tangent here, so I can peel one tangent off also. So if I take one of the tangents here, peel it to the side, that'll be tangent to the 4th. If I take one of the secants and peel it off, I'll have secant squared. And then I pulled the tangent and the secant. So that good? One factor of each is just pulled off to the side. And now I recognize that as being the derivative of what? Secant, right? This is a derivative of secant. So now if I can somehow rewrite this in terms of secants, I'm in business, because that's the derivative of secant. So this is already secant, and I have tangent to the 4th here. So tangent squared squared, right? So, yep. So this is going to become tangent squared of x squared, secant squared x, and then let me rewrite this as secant x tangent x dx, just because I can, and that looks a lot like up there. And now rewriting tangent squared using the Pythagorean identity. So I come over here to tangent squared x, solve for it, which means I'm going to replace tangent squared x with secant squared x minus 1. So I have, in parentheses, secant squared x minus 1, that quantity squared, times secant squared x times secant x tangent x dx. Okay.
I killed a lot of trees doing the homework.
Yes. So I have a philosophy on trees.
Oh man, here we go.
Yeah. I got in trouble a few years ago when I married my wife over 10 years ago, and when we first got married, moved into a house, and we had the recycle stuff. She was real big about let's recycle, and so she found out that I was putting the recycle in with the trash, and she got all upset. So we had to have a sit-down conversation about recycling. So I believe that we waste more energy recycling than we actually gain. Like, that's just my opinion. You can have yours. But I will say that at the end of it all, the sun will recycle it all, so it won't matter, right? Yes?
Happy wife, happy life, so just recycle.
I agree with that. Yeah. No, I do now. I do recycle now,
right,
okay?
right.
But I still had to state my purpose, yeah.
Make your case.
Okay, yeah. Okay, so what are we doing here? At this point, we've got, this is the derivative of secant, and we've got everything written there in terms of secant. So I'm going to write u is secant x, and du is secant x tangent x dx. And now we just rewrite this, right? So what's our new integral this time? In terms of u, it is u squared minus 1, that quantity squared. And then I still have secant squared, right? So u squared again. And then the rest of it is just du. And could y'all handle that now?
Yeah.
Yes? Okay, just, you would have to expand that, right? FOIL it out, then distribute a u squared, then do term by term, power rule. Yes? ... Okay. All right. So it seems like this is very much, well, it's like what we did before when we had sines and cosines. We'd peel off a cosine or we'd peel off a sine because it's the derivative of sine or cosine. Then we try and rewrite the other stuff and make a substitution. This is the same game, all right? Just we're dealing with tangents and secants now. All right. So since it's so similar, I'm not going to do any more examples. But there are some other cases, all right, that we may run into that aren't so obvious. And we're going to need some knowledge of common identities. We might need integration by parts. And my favorite part of this, just some persistence, all right? Persistence is something in this class that hopefully you're developing. All right, so here are some integrals I want to do. First one, tangent x. So we know what the derivative of tangent x is, right? But what's the antiderivative? So look on your formula sheets, because guess what? Your formula sheets have it. Looking in the antiderivatives, it should show you the antiderivative of sine, right? It's there. Antiderivative of cosine, antiderivative of tangent, antiderivative of secant, cosecant, cotangent. All 6 basic trig functions, the antiderivatives are supplied, right? Okay, but how did they get the answer? Because the answer should be natural log of the absolute value of secant of x, right? Okay, so where does that come from? All right, so we look at this, and you can't peel anything off, right? You don't have secants and tangents, you just have tangents. So you can't peel anything off. So how about we do this? Let's go back and do the thing that we kind of always fall back on this when nothing else works. We rewrite tangent in terms of sine and cosine, right? And that's what it is. And now, what do you see we can do here? Basic u sub, because you see something in its derivative, right? Okay, so what's going to be the u sub that you're going to make here? U is what? Cosine. Why not sine?
Because the derivative would be in the denominator.
That's right, because if you let u be sine x, the derivative cosine is down on the bottom. Remember, we always said it has to be on the top. It can't be trapped, right? Okay, so we want to let the u be the cosine x. And then, of course, the derivative of that is negative sine x dx, which we almost have. We have sine x dx. We don't have negative, so we just multiply both sides by -1, right? And now we can rewrite the problem. What does this rewrite to be in terms of u? 1 over u. So integral 1 over u and then negative du, right? So how about I put the negative on the outside and just put du here? Yeah, and now you should recognize that antiderivative 1 over u is natural log of the absolute value of u. So I have negative natural log of the absolute value of u plus c. And what was u? It was cosine x, right? Cosine x. That's not the answer on the formula sheet. Did we mess up? No, we didn't mess up. How are we going to get this to be natural log of secant x? The negative out front's like a -1, and we're using properties of logs backwards, because usually we take powers and bring them out front. But what if I put that power back up? It'd be natural log of the absolute value of cosine of x raised to the -1, not arc cosine. This is taking the cosine function and raising it to the -1, which is not the same as the inverse. So that's the same as 1 over cosine, isn't it? And that's secant. 1 over cosine is secant. So this becomes natural log of secant of x plus c. Yes?
So it's not the antiderivative, it's the rule where you...
Using the rule, natural log of x to the n equals n times natural log x. That's a property from college algebra, that we could pull powers out front. We're doing it backwards. We're taking the number that's out front, pushing it up as the power on x. So it's becoming the power on the cosine. All right? Do you see how you could probably do cotangent the same way? Like if this was cotangent x, this would be cosine over sine. And then you'd let u be sine, and then it should work out, right? Okay. So thumbs up on you could do cotangent? Yes? Thumbs up, you could do cotangent? All right. How about this then? This is one of my favorites in this section. Now this is on your formula sheet, right? And look at the answer to that. Whoa, right? Like what?
It's the same application though.
Is it though? Can we do this the same way?
Make that secant x, tangent x. No, sorry. Disregard.
I think what we could do this, right? We could do that, but why won't that work?
Can't do substitution.
And you can't do a u sub because you need something in its derivative there, right? It's not there.
Well,
How about integration by parts?
there's no product.
That's okay. We've had problems like this before. There was a problem on your test. No? Yeah, on your test. Wasn't this on your test? Right? And we did that with integration by parts. And we let u be that, and we let dv be that, dx. So there are ways, maybe. Okay, should we try it? Okay, basic u sub is off, right? We can't do that. No basic u sub. So let's go from here. Let's do integration by parts. U is equal to, well, we only have one choice, secant x, right? And then dv has to be dx, okay? So then what would du be? Derivative of secant x is secant x tangent x dx. And then what would v be? X. Okay, look at voodoo. Look at voodoo. Is voodoo something you feel like integrating? Voodoo. X, secant x tangent x.
Particularly.
It's gotten worse, hasn't it? Because you still have trig stuff in here, but now you've got an x in there also. We've always wanted this integration by parts to get us something nicer, right? Easier to deal with, but it's not. We've introduced now this x power. So without us going through and trying, this is not going to work, okay? This is not going to work. All right, you ready to see it? Okay, so this is not a technique. This is not like integration by parts or u substitution or this thing with Pythagorean identities. This is somebody sat here with this problem long enough and figured out this would work. Okay, so here it is. You ready? So I would never expect anyone here to get this, but now that you see it, you're going to be like, oh, wow, okay. So what we're going to do is we're going to take this and we're going to multiply it by 1. But the one that we're going to choose is secant x plus tangent x over secant x plus tangent x again. All right, dx. Is that the same problem? Is it natural for you to come in with that one? No, right? Like you would never think to do that, yes? Okay, but it's going to work. So let's see how it works. Let's go ahead and distribute the secant here through the top, okay? And then we would get on top secant squared x plus secant x tangent x over secant x plus tangent x. Are you all following what I did? Yes? Okay, does anyone see it now? We're there. Basic u sub. What's your u? The denominator. Look at that. Look at this right here. If we call that u, what's the derivative of this? Well, what's the derivative of secant x? Secant x tangent x plus, what's the derivative of tangent x? Secant squared x. The derivative of the bottom is now at the top, right? So just basic u sub. So u is going to be secant x plus tangent x, which is the denominator. The derivative of that is secant x tangent x plus secant squared x dx, which happens to be the numerator. Beautiful. So this now becomes integral 1 over u du. There's not even a negative sign or anything. It's like perfect, isn't it? And the antiderivative of that is just natural log of the absolute value of u plus c. And then we replace u with secant x plus tangent x. And that should match the formula you have, right? So I guess the question is, like, who came up with that, right? And that's what mathematicians have to do. They have to figure out a way sometimes. And just, I'm sure somebody struggled with that for a while. Maybe months or years, I don't know. But for us, it's, you know, a couple of minutes here. We appreciate someone did that for us. And now we have a way of finding the antiderivative of secant by itself. How about cosecant? Do you have a formula for cosecant? Cosecant can be done in a similar fashion. I'm not going to go through it, but it can be done in a similar fashion. So that means we actually, now, we can find the antiderivative of sine, cosine, right? Those we knew coming in. And then tangent, which we did just a second ago. Cotangent, we didn't do, but we said we could do it. And then secant, I just showed you, and cosecant, I said, can be done similarly. So we've got all 6 trig functions, antiderivatives, taken care of. All right, so that one definitely worked out a little bit weird, yeah? Okay, how about this one? This next one is so unassuming, but then it turns out to be such a weird problem. Again, it's on my top of my list for this section is problems I like. It's just such a, just the way it works out is just so interesting. Now this one is not one where you need to come in with this weird, like, one that you would have never thought of. This one you can do with what you know. All right? The question is, how are we going to do it? So, any ideas? Wrong. No, I'm sorry. What?
Pull a secant x out.
Pull a secant x out. Okay, let's try that. Now, you want me to pull one secant x out?
Yes.
You want the secant, you want me to write secant squared, then secant? That's fine, I'll do it.
Fine.
Okay, so I'm just going to follow your lead. Okay, we all agree you could do that? Yes? Okay, now. What would you like me to do now? Tangent squared x plus 1. You could rewrite the secant squared as tangent squared x plus 1, but then what would you do with that? Because if I make this stuff tangent stuff, right? Then are you going to do a u sub of tan? Because the derivative of tan is not secant, it's secant squared. So this is not the derivative of tan. That's the derivative of tan, isn't it? Tangent x?
You can do u substitution with secant x.
So if u is secant x, what's the derivative of secant x?
Tangent x.
Secant x tangent x,
Oh, secant.
which we don't have, right? We have a secant x, we don't have a tangent x.
I thought the derivative of secant squared x is
No. No, the antiderivative of secant, yeah. Okay, something else?
Can you separate the tangent after you rewrite it?
Separate the tangents.
Tangent x squared.
You could go tangent times tangent, yes. But you'd still have plus 1. Let me just write it down. Tangent squared x plus 1. This is what we would be looking at right there, right? That's what we'd have? And then you're saying make that tangent times tangent? Okay, I see what you're saying. So you're saying rewrite that as tangent x times tangent x. And then you want me to distribute this? No? Okay, secant x plus secant x dx. I guess that's what you're saying? It doesn't work because this right here, secant x tangent x, is the derivative of secant x, but that's a tangent x, so it's still not going to work. I heard someone say it, so I don't know where it came from, but integration by parts? Okay, how?
Take secant squared x as your u.
You want secant squared x as your u? What do y'all think? Okay, so if I let secant squared x be my u, it's going to go here, right? And then I take derivative of that. And then what's going to go here? And I'm going to have to do the antiderivative of that. So I think if this is secant squared x, I have no problem taking the derivative. It's not going to be pretty. But then if I put secant x here, I need its antiderivative, which we know it because we just did it, didn't we? But wasn't it like natural log of all this stuff? And then my voodoo is going to be natural log of a bunch of stuff times something that's really ugly. So maybe the other way.
If secant x doesn't work, could you just do dx? Because then the antiderivative of dx would be x.
Yes. But then u would have to then be secant cubed, wouldn't it? So just switch them. You're there, but you just have them in the wrong place. This right here goes secant x. Just secant x. And this one here, secant squared x. Why is that okay to have secant squared x here? Antiderivative of that's tangent. Okay? Right? Okay, let's go with this. What's the derivative of secant x? Secant x tangent x dx. And then the antiderivative here is tangent x. So this voodoo doesn't look as bad as maybe if we had done it the other way around. Are you all following this? Let's just keep going, see what happens. What is the new integral going to be?
tangent x minus integral of
Okay, so this right here is equal to ultraviolet, so secant x tangent x.
minus integral of tangent x times secant tangent.
Yep, tangent x times secant x tangent x dx. So I'm going to write that as tangent squared x, right? Secant x dx.
So we could do tangent squared x, the identity is secant squared x minus 1.
We could replace tangent squared x with secant squared x minus 1, couldn't we?
Yep.
Now, I don't see anything as far as like peeling things off. Like this secant x dx is not the derivative of tangent, so we can't do a basic u sub here. Agreed? So let's just stick with that and see what happens. We have this is equal to secant x tangent x minus integral, replacing tangent squared x with secant squared x minus 1, right? That's this. And then times secant x dx. But now we've got a bunch of secants in there. I mean, it almost seems like we're just going in a loop here.
U substitution at this point.
What's your u?
Secant.
What's the derivative of secant? Right, you're missing the tangent, that's what I'm saying. But it's okay, let's keep going. I'm going to rewrite this. Isn't this secant cubed x minus secant x dx? Isn't that what that is? Just distribute the secant through, right here, secant. Do y'all see it? What do you see? What's that?
Seems like this is what we started with.
Kind of, right? We were trying to do the antiderivative of secant cubed.
You could factor out a secant maybe.
Well, that would take us back to here, though.
That's true.
So wait a minute, hold on. Let me write this down. Are we saying that the antiderivative of secant cubed dx is equal to secant x tangent x, watch this, minus integral secant cubed x dx plus integral secant x dx. Is that what we're saying is happening right now?
Yes.
That integral is equal to this minus that minus minus plus that. So I'm separating this into two integrals, right? Now do you see it? This has happened one time before to us, where the integral we were looking for actually appeared over here again. Do you see it? And we can bring it back over. Now, we still have this one, don't we? But we did that already, didn't we? The antiderivative of secant x is natural log of secant x plus tangent x. So we already know the antiderivative of that. So this becomes, let's see, we add this integral. And we add this integral over here. We're adding one of them, right? So how many of those integrals will we have? Two of them, right? So two of the integrals we're looking for is equal to secant x tangent x plus natural log of secant x plus tangent x plus a constant. I'm almost there. So this is this. This part went over there. This we did in the problem before. And so there's one more step. One more step. One more step.
Take the integral of secant x dx.
Just all we need is that number gone, right? We have two of them, we just want one of them. So just divide everything by 2. So that means our final answer is going to be that the integral of secant cubed x dx is equal to 1/2 secant x tangent x plus 1/2 natural log secant x plus tangent x plus c.
Can you tell me how you got rid of that constant?
I divided by 2. I divided this whole side of the equation by 2, divide that by 2, divide that by 2, and then any constant divided by 2 is still a constant. And then I just put it as 1/2 in front. So, yeah, you can see why I like that problem. It's kind of a cool way that works out. All right, how do y'all feel? This okay? No? Yeah, so you get to go play with the homework and have fun with that. We're halfway through this section. And now we go into the second half. All right, so I remember when we started this section, I said we're going to be doing 2 basically different ideas, but you can't do the second half unless you're good with the first half. This is the first half, all right? So now in theory, if we see combinations of sines and cosines, tangents, secants, things like that, we should be able to take care of it. Yes, in theory? Yeah? Okay. Okay. So before we get into the second half, I'm going to just put up a problem right now, and we're going to see what we can do to it. Okay, so we have not seen anything like that yet. Next to this one, don't write this down. I'm going to put this one. Which of those two could you do easily? The one on the right. Why? Basic u sub. U would be 1 minus x squared, the derivative of that, negative 2x dx, right? Which you have an x out here, so you'd be able to play with it. You know, you could get that one, right? Basic u sub. Can't do basic u sub here, because if you let the inside the radicand be u, the derivative of that has an x in it, and there's no x sitting there, right? So basic u sub's not going to work. What about integration by parts? What about integration by parts on this one? You only have one choice for u, right? You have one choice for u. What would it be? U would have to be the square root of 1 minus x squared. It would have to be. And then dv would have to be dx. And so if you take derivative of that,
1 over 2.
Yeah, du would be 1 over 2 square roots of 1 minus x squared times the derivative of the inside, negative 2x. And then the negatives cancel. So you wind up getting something like x over the square root, sorry, negative x over the square root of 1 minus x squared. Agreed? That would be the derivative of this. And then what would v be? X. And so look at the new integral. The voodoo integral would be this times this, right? Which would turn out looking like x squared over square root of 1 minus x squared dx. And there's a negative I took out. I'm just trying to get like a big picture of things. This is the new integral, right? And that integral sucks, right? That's worse than what we started with. Can't do a basic u sub here. Okay, you're stuck. Okay, so no basic u sub, no integration by parts. What else do we have? Oh, well, we can do sine, cosine, tangent, secant, right? We can do that stuff. But this doesn't have anything, right? This doesn't have any sine, cosine, tangent, secants, right? So we are stuck. Yes? We are stuck. All right. So from this idea of this next concept, this second part of this section comes from the idea of we struggle with square roots of binomials like this. Whenever we see things like that, 1 minus x squared, or if that was like 1 plus x squared, or maybe if it was x squared minus 1, you know, any of those, we have trouble with them. And so what we're going to do, and I'll give you the steps. Okay, I'll give you the procedure in a second. But right now I just want you to see it first. What I'm going to do is I'm going to make a substitution. Now, prior to this, let me give you a problem here so you can see what I mean. Let's say we had this problem right here. This I could do with basic u sub. U would be x squared, and then du would be, 2x dx, and then that would become basically 1 over sine u, which is cosecant u, and we could do that, right? Okay, so when I make a basic u substitution, what I'm doing is I'm taking a complicated expression, that's not very complicated, but I'm taking a complicated expression and replace it with a simple expression, right? What I'm about to do is completely backwards from that. I'm going to take a simple expression and replace it with a complicated expression. Yes?
Just curious.
Yes.
Would you be able to switch the integration by parts where your dx would be your u? And then
No one has asked that. Why have I never done this in the problem? I guess this is what you're saying, right? Something like that?
why would you write it as like u or 1 minus x squared with the negative half?
Okay, yeah, but same thing. You would have this here. The reason this can't be done this way is because, first of all, what's the derivative of the derivative, right? We have to take derivative of this, right? So you're going to get the second derivative, right? And then you have to integrate this, but this doesn't have a dx in it. And so you can't integrate without that differential in there. So it's just not going to work. I'm glad you asked. No one has asked, and I've thought about it several times. But I've thought about mentioning it, but I haven't. So, Okay, so you ready? I'm going to make a substitution, but instead of taking something complicated there and replacing it with u, I'm going to take something simple there and replace it with something complicated. Ready? Okay, I'm going to make a substitution right now. Everywhere I see x, I'm going to replace it with sine theta. All right? Okay, that's the substitution I'm about to make. Now let's see what happens. Well, what is x squared then? Sine squared, okay. So I'm sitting here, this step right here, this right here, let this happen, okay? I've got a little bit of a, they call that a God complex, right? You're just kind of like, you're just letting it be, all right? You are making it happen. You are choosing to do this. X is going to be sine theta, and now I rewrite everything. X squared is sine squared theta, right? What would 1 minus x squared be? So what I'm doing is I'm trying to rebuild this right here. X is being replaced with sine theta, so this is going to be sine theta squared. Then what's 1 minus that? Well, that's 1 minus sine squared theta, right? But what's 1 minus sine squared theta? Cosine squared theta, isn't it? Okay. But then what's the square root of 1 minus x squared going to be? Well, that's the square root of this, right? Which is the square root of this, and what's the square root of cosine squared? Yes? Just that, right? Okay, so let me get this straight. We had this nasty thing. If we make this substitution that x is sine theta, then that big ugly thing is just going to turn into cosine theta, isn't it? Right? Yes. It is. We have certain restrictions that we aren't going to consider because of the, well, let me work through it first, and then we'll talk about the absolute value. Okay? Very complicated expression should turn into this, right? But there's one thing I haven't addressed. The dx. Okay, well, if this is x, then can't I just take derivative on both sides? So what's the derivative of the left side of that? Dx, right? What's the derivative of the right side? Cosine theta d theta. So this is kind of like what we were doing earlier when we had u was like x squared. We take derivative of the left, derivative of the right, right? This is what we were doing earlier. But now I'm doing it with x and sine theta. So derivative of x is dx, derivative of sine theta is cosine theta d theta. Follow? Yes? No? Yes? Y'all look stunned or happy. I'm not sure what that is. So what does this integral now become?
Cosine theta.
This right here is cosine theta, right? So cosine theta, cosine theta times dx, which is cosine theta again, d theta. I've rewritten the whole integral in terms of theta, haven't I? And that's cosine squared. Theta d theta. And can you handle that? Yep. Jordan? Where's Jordan? Jordan, so how would we handle that cosine squared, Jordan? Power reduction formula, okay? Power reduction formula. So this, we're going to use that, it becomes 1/2, and then what? 1, is it plus or minus? For cosine, it's plus cosine of double the angle, right? 2 theta d theta. Is everybody following? Do you see what I'm saying? How you can't do these problems if you can't do these? Like I can't do this if I can't do that, right? Okay, so now get to here. I'll pull the 1/2 out. Integral 1 plus cosine 2 theta d theta. And now I can integrate each of those term by term. Carefully, Jacob. Where's Jacob? Okay, Jacob. Antiderivative of each one of those terms, Jacob. I'm going to leave the 1/2 out here. Antiderivative of 1 here? And anti, not x. What's our integration variable? Theta. So the antiderivative of 1 is theta, right? In this case, theta. Plus, okay, antiderivative of cosine 2 theta. We'll stick with you, Jake. Antiderivative of cosine 2 theta. 1/2. 1/2 what? Sine of 2 theta. Yes? Yeah, we're getting there. We're getting there. Yeah, plus c. Okay? Do you all agree we've actually done an integration? Okay, now we have to get back to where we started because we started with a problem in terms of x. And we've now got an answer in terms of theta. So we've got to somehow get from theta back to x. Yes? We're going to use this, yep. We're going to use this thing that we used right here. But I'm going to do it kind of a slightly different way. Well, not different, just the way I do it. I don't know. I'm going to leave that right there because that's our answer, right? And I'm going to leave that there because that's what we started with. So right now, two things we need to know. We need to know what theta is, and we need to know what sine of 2 theta is. Yes? Those two things we need? Okay. The only thing I know that connects x and theta together is this right here, right? Which is the thing I came up with in the very beginning. I didn't tell you why I did it, right? I just said, let's do it. So if I look at that equation, do you agree that there is a right triangle that I could draw that goes with that? In other words, if I call theta this angle, sine is which side over which side? Opposite over hypotenuse. Then if I label that x and that 1, then that triangle goes with that equation, right? Yes? Okay. And then, what? Yeah. Is it delivering on the promise here that you basically need everything? Like you have to have everything here, yes? Okay, so we can get this side, right? I don't even know if I need this side, okay? Everyone, I don't even know if I need it, but I can get it, can I? Okay, so that's square root of 1 minus x squared. Coincidence? No. Okay, so let's keep going. Let's keep going. What's theta? What's theta? What's theta? What's theta? Okay, theta, I heard someone say inverse, right? So if I am working with that equation, let me get this out of here. If I'm working with that equation, someone asked me to solve for theta, I could just simply take arc sine of both sides, right? Arc sine of both sides. I don't know why I put theta there. That should be x. Okay. Now, remember, if we're bringing arc sine in, we're restricting theta, aren't we? Because arc sine is only defined from negative pi over 2 to pi over 2. So we have some restrictions. So remember how you're asking me about the absolute value? We don't need it anymore because now that we know that we're in this, cosine's always positive here. So you don't, back when we did square root of cosine squared theta, that right now we can say is cosine theta because now we know theta is restricted between here and here. So cosine's always positive in these two quadrants. Is that enough for me to go past this now? Yeah. Okay, it was a very good question. Because technically, everyone, algebraically, the square root of x squared is the absolute value of x. Always. Unless there's some restriction on x that you're aware of. What we know here is that this answer in here, cosine theta, before you square it, we know that it's positive because we know the restriction here when we do the arc sine. Okay, moving on. We know what theta is, yes? We know what theta is? Got that? Check. Do we have theta in terms of x? Absolutely. Theta is in terms of x. All right, next thing, I need to know what sine of 2 theta is. Well, here's what I know about sine. Sine of theta is x over 1, right? But we want sine of 2 theta. Okay, well, we took pre-cal. And we know that sine of 2 theta, there was a formula for that. That's 2 sine theta cosine theta. Remember that? That's double angle identity. Remember that identity? The great thing about that identity is that instead of working with 2 theta, it works with theta theta, right? But you have to have cosine and sine. Do we know sine of theta? Yeah. Do we know cosine of theta? Absolutely, because we have a triangle. Cosine is adjacent over a hypotenuse.
So how did you get 2 sine theta times cosine theta?
This is an identity from pre-cal. This is a double angle identity. Yeah, it's on the formula sheet, and this is one of those ones you should star and probably put here, because it does come up quite a bit now. All right, so you ready for our answer? Okay, good. You sound enthusiastic about that. Okay, so here we go. We have equals 1/2. Okay, parenthesis. What was theta? Arc sine of X, right? Plus 1/2, right? Half times 2, so the half and the 2 are going to be gone. And then we have sine theta, which we know is X, times cosine theta, which is off your triangle, square root of 1 minus x squared. And that's the end, right? Yes.
Where did you get the x from?
Okay, let me do this. Okay, so this, okay, the 2's, the half and the 2 cancel, right? Okay, so sine of theta, sine of theta is x. Now you're asking where does that come from? It either comes from here or it comes from here. Sine is opposite over hypotenuse, right? And then cosine theta is that piece, and that comes from this right here, adjacent over hypotenuse. So you see I did need that side, didn't I? I actually needed this side because that gave me what cosine is. That's it. You tired today?
Don't erase it yet.
You tired? I'm tired too. Gotta stay awake though. If you need to go walk in the hall, that's fine. You're missing something really, this is important stuff right here. And I'm seeing you sleeping, and you're gonna regret that. Yes?
Could you have solved this in a similar fashion if you would have done cosine instead of sine? Or would it have caused...
Well, okay, so let me ask you, you think it would work with cosine? Let's think through it, right? If you replace this x with cosine, then you're going to get 1 minus cosine squared, which would become sine squared, and the square root of sine squared would be sine, right? So this would have become a sine, and then over there you would have had dx, you would have taken the derivative of cosine, you said? No, you said you want to replace, and it would do that, you get sine, so you get like a sine squared, and it would work, yes, it would. The work would almost be identical. It would be kind of the same stuff. All right, answer? Happy? Not happy? Do you believe that that's the answer? Did you do it yet? Did you try it? Okay, so look, let's take the derivative real quick. Okay, if I take derivative of this, I better get back that. What's the derivative of arc sine of x? So derivative of that's 1 over the square root of 1 minus x squared, right? And then I have a half in front of that, so I'm going to put a 2 down there. And then plus, I need to take derivative of this, which means product rule. Derivative of the first one is 1 times that. You know what? I'm going to take that 1/2 out. Just leave it out here. Okay. So derivative of that times that plus, what's the derivative of the square root of this? Well, didn't we do that a second ago? Didn't that turn out to be like negative x over square root of 1 minus x squared? That's derivative of this. But then times that, because product rule, so that's going to become x squared. And that's it, right? It's 2.
Didn't you say the 1/2 cancel when we... Sorry.
Yeah, so when you take derivative of this, we did that a second ago. It was 1 over 2 square root of 1 minus x squared times derivative of what's inside, which is negative 2x. The 2's cancel, you get a negative x up there, but then you have to finish the product rule off, so you have a negative x squared. Yeah, so that's this piece. Yeah? Is that right? It may not look right to you, but hey, check this out. That's a fraction, right? Okay, so let's get a common denominator. What's my common denominator? That right there, right? So I'm going to make this square root of 1 minus x squared by multiplying the bottom by it and the top. When I multiply the top, what happens? The root goes away. Okay. Now, these all have the same denominators. So let's put them all together, all the numerators. 1 plus, or minus, I should say, x squared minus x squared. Hold on, something's...
So we would have 2 over square root of 1 minus x squared.
Oh, yeah, okay, hold on. All over square root of 1 minus x squared, right? There's a half in front. Okay, I didn't see it at first, but that's 2 of these minus 2 of those, right? So now that's half. We've got 2 minus 2x squareds over the square root of 1 minus x squared. Pull the 2 out, cancel it with this. I'm going fast because we don't have time for this shit right here. Okay, that, and then this right here is the same as, well, the same as x over root x, which is just root x. They're the same thing, right? So this is that. Okay, so it works. But what did I do in the beginning?
You made it complicated.
I took something that was not that bad and something simple, and I made this substitution where I replaced that simple x with something with trig in it, right? I took a simple x and replaced it with something with trig. And so what we call this is trigonometric substitution, or trig sub, okay? So that is what this second part of this section is about. 6.2, trigonometric substitutions. So after we master the above concepts, we can use them along with an interesting type of substitution to find antiderivatives of rather complex functions. These new types of substitutions are called trigonometric substitutions or trig sub. So now we have all the basic antiderivative stuff that you should have known coming in here, like the antiderivative of cosine and sine. We have the power rule. We have integration by parts, right? We have trig integrals, integrals that involve trig stuff, sine, cosine, tangent, secant, and now trig substitution. Here's the general idea. If we ever see in our integrand, anywhere in the integrand, the square root of a constant squared minus x squared. So the one we just did was 1 minus x squared, right? So what was a for us? A was 1, right? Minus x squared. If we ever see that, then we are going to make the following substitution. We will replace x with a times sine theta. So in the previous problem, because that number was a 1, I just did sine theta, right? But what would happen if I would have done, what if our original problem was 4 minus x squared dx? Then what would the substitution be here? 2 sine theta. That would be the substitution. Okay? What would happen if you had square root of 3 minus x squared dx? What would your substitution be? X is going to be root 3 sine theta. Okay? So it's like whatever number's here, you have to take square root of it, and that's your a. Square root of that is 2. When we had a 1 there, square root of 1 was 1. Okay? Now, why do we make the substitution of x is equal to a sine theta? Why does it work? Well, because then if we take the original expression and we replace that x with a sine theta, then it becomes this, right? We can factor an a squared out of the root, or out of these two terms. That 1 minus sine squared theta then becomes cosine squared theta, and then this thing becomes a cosine theta. Every single time. Every time. All right? So in other words, if I'm looking at this problem right here, right, and I make the substitution, x is equal to 2 sine theta, what can you tell